So now we're going to look at solving polynomial inequalities and rational inequalities. And so solving nonlinear inequalities, we go about this a little differently than what we did when we were solving linear inequalities. We're going to look at this both graphically, and then we're going to look at it when we're given an inequality, the inequality itself, and solving it. So let's see what's going on graphically before we talk about what's going on or how to solve it if we're given the inequality itself. So in front of us right now, we have two different graphs. Let's look at the first graph up here. And looking at the first graph, part A states that we want to find f of x when f of x is is less than 0. So if we're looking at when f of x is less than 0, so we're given the graph of f of x. If f of x is less than 0, this is telling me that the graph is falling below the x-axis. Those values of x are giving me back a negative value. And so we want to find the pieces of the graph where we're below the x-axis. And so we're below the x-axis here. Notice when x is less than -1. I'm sorry, that's not below. That's above the x-axis, isn't it? When x is between -1 and 1, and when x is bigger than 1. Those are the values where my y values are negative. They're less than 0. And so when we're looking at the solution, we're looking at all the x values that give us this. And so looking at all the x values that give me this, it's everything again between x equals -1 and 1. I'm putting a parentheses, I'm writing it in interval notation, so parentheses -1, comma 1, parentheses. If it had less than or equal to, I would include the values where it was touching or crossing the x-axis. But it was strictly less than. So union, everything bigger than 2, so parentheses 2 to infinity. Another way that you could have written this, if it was inequality notation, you could have said this was -1 is less than x is less than 1, union x is greater than 2. For the next piece, it wants to know when is f of x greater than or equal to 0. So these are values where it is above the x-axis, and it wanted equal to 0, so it's also the values where we're touching or crossing the x-axis. So again, we want the x values that are giving us those. So looking at this, everything from -infinity up to -1, including, so we're going to put a bracket, union, then we're looking at everything including and in between 1 and 2. So bracket 1, comma 2 bracket. So I would state this in an inequality form as x has to be less than or equal to -1, union, or x is between, so 1 is less than or equal to x is less than or equal to 2. So notice here, these values where it crosses the x-axis or touch the x-axis were important values. This is where our graph changed signs. And we're going to use that fact when we start solving these inequalities given the inequality in the graph. We'll talk about that in a minute. Let's look at one more example. In this next example, notice we have a graph. We have a horizontal asymptote. It looks like at y equals 1, and we have two vertical asymptotes, x equals -1 and x equals 2. So for the first piece, we're looking at values where f of x is greater than 0. So f of x is greater than 0. That's going to be values where our graph is above the x-axis. And so again, I'm looking at values where I'm above the x-axis. So on the left of my vertical asymptote, x equals -1. Notice I'm up there in the second quadrant. My y values are positive. Values between -1 and 1, I'm above the x-axis. And then values greater than 3, I'm also above the x-axis. So f of x is greater than 0. On the interval, I'm using my x values from -infinity to -1. Remember, I can never cross a vertical asymptote. It's undefined there. So I need to put a parentheses and not a bracket on -1. Union from -1 to 1, not including -1 and 1, and union parentheses 3 to infinity. If I was to state this as an inequality instead of interval notation, this would have been x is strictly less than -1, union -1 less than x is less than 1, union x is greater than 3. Looking at part B, we're looking at where is our function f of x less than or equal to 0. And so these are values where it's equal to 0. So those will be values where we're touching or crossing the x-axis. And values where we're below the x-axis. And so looking at my graph, f of x here is greater, I'm sorry, not greater than, it's less than or equal to 0. So we can include 1. So I'm going to put a bracket 1. I'm getting closer and closer to 2, that vertical asymptote, but I'm never going to touch or cross it. So parentheses. And then union parentheses 2. And then at 3, I'm touching the x-axis. So I'm going to put a bracket. So that would be the interval notation form of where f of x is less than or equal to 0. To write this in form of an inequality, I would have 1 is less than or equal to x is less than 2. Union 2 is less than x is less than or equal to 3. So I want you to notice in this case that where the graph crosses, or not crosses, where you have a vertical asymptote, our graph can actually change. It doesn't in this case. It could change where it's above or below the x-axis. And so we also want to worry about checking the values on either side of vertical asymptotes besides looking at our x-intercepts when we're dealing with rational functions. So now in front of us are steps for solving a polynomial on rational inequalities algebraically. So we just looked at it graphically. Now we're going to look at it algebraically. So when we're solving these algebraically, first thing that we want to do is we want to rewrite our inequality so that everything is on one side of the inequality and that it is either greater than or equal to, less than or equal to 0. So step 1 says, write your inequality so that the polynomial or rational function f is on the left side of the 0. And it is 0 is on the right side in one of the following forms. F of x is greater than 0, f of x is greater than or equal to 0, f of x is less than 0, or f of x is less than or equal to 0. If it's a rational function, we do not want to clear the fraction like we were doing when we were solving rational equations. And that's because you would be getting rid of your vertical asymptotes. And vertical asymptotes are something that we'll be looking at. And you'll see that when we're going through this, but let me continue reading. So for rational functions, be sure that the left side is written as a single quotient and find the domain of f. Do not clear your fractions. So that is one of the most common errors that I see when I'm grading the work for this stuff. So do not clear fractions for rational inequalities. So once we've gotten everything to one side of our equation, if it's a rational function and we rewrote it as a single fraction if it hadn't already been so, then what we want to do is we want to find the values which set our function equal to 0. And if it's a rational function, we also want to find where our function is undefined. So values which set our denominator equal to 0. So step 2, we're going to determine the real numbers at which f of x equals 0. And if the function is a rational, then the real numbers at which the function f is undefined. So once we find these values, I call these values our critical numbers or critical values, we're going to place these on a number line. So use the numbers found in step 2 to divide a real number line into intervals. Okay, so I'll write a number line and I'll put those special numbers we just found in step 2 on a number line, and that will create multiple intervals on that number line. And then the next step is I'm going to test one value on each interval between those critical numbers we just found. And I'm going to plug it back into my inequality to see if I have a true or false statement. Okay, so step 4 says select a number in each interval and evaluate f at that number. If the value of f is positive, then f of x is greater than 0 for all numbers of x in that interval. If f of x is negative, then our function f of x is less than 0 for all numbers of x in that interval. If the inequality is not strict, so we have the equal part for our inequality, we have greater than or equal to or less than or equal to, we want to include the solutions of f of x equals 0 that are in the domain of our function f in the solution set. We got to be careful though, because we're never going to include values which set our denominator equals 0. So if we had the less than or equal to or greater than or equal sign in the inequality, we will just use the solutions that set the equation equal to 0, but not also the denominator. So be careful to exclude values of x where f is undefined. So undefined again, values where your denominator equals 0. So 4.5 in our textbook was quadratic inequalities. Quadratics are not linear. So we would be following the same process that we are doing right now to solve these quadratic inequalities. So let's go through and look at some inequalities and solving these algebraically. Okay, so looking at the example in front of us, x squared minus x minus 12 is less than 0. So our first step is done for us, where everything is on one side of the inequality and it is 0 on the other side of the inequality. So that step is done for us. And now we want to look for our critical numbers. We want to find the critical numbers, which again were the values where this was equal to 0. So find our critical numbers. And so that's where x squared minus x minus 12 is equal to 0. So looking at this, it's quadratic. You can approach this in whatever method that you want to do. Personally, if it's factorable like this, which it is, I would factor it, but that's your call. You can do the method of your choice. So looking at the two numbers that multiply to -12 and add to -1, I notice I have -4 and +3 are those two numbers. And so x squared minus x minus 12 factors as the quantity x minus 4 times the quantity x plus 3, and then that's equal to 0. So setting each piece equal to 0, we're looking at when is x minus 4 equal to 0, and when is x plus 3 equal to 0. Solving for x in each case, this is when x is equal to 4, and this is when x is equal to -3. Okay, so those were the critical numbers. So the next step was place your critical numbers on a number line. So my smallest critical number here is -3, and my largest critical number here is 4. And so notice I have 3 separate intervals. I have this interval in here where x is less than -3 that I need to test. I have an interval in here where x is between -3 and 4 that I need to check. And I have an interval where x is greater than 4 that I need to check. And so we want to choose any number that is strictly less than 3. So how about x equals -4? So we want to plug in -4 into our inequality and see, is this a true or a false statement? So if we go in and wherever we see an x, we plug in -4, we want to see, is that less than 0 or greater than 0? And so I have -4 quantity squared minus a -4 minus 12. Is that less than 0? Well, -4 quantity squared is 16. 16, and then I have negative, minus a negative is plus. So +4 minus 12. Is that less than 0? Well, I notice that I have 20 minus 12, which is 8. 8 less than 0. This is no. So this is positive. It's above the x-axis at x equals -4. This is not going to be part of my solution. And so no number less than -3 would have worked, plugging that in the inequality. So now looking at this, choose a number between -3 and 4. If 0 is always in that, if 0 is in that interval, it's always the easiest number to choose. And so I'm looking for a number of x that falls between -3 and 4. X equals 0 works. And so I'm going to go back into my inequality. I'm going to go in and plug in 0 wherever I see an x and see if I have a true statement or not. So 0 squared minus 0 minus 12, is that less than 0? Well, yeah, -12 is less than 0. So this is a true statement. So that tells me that any number in between -3 and 4 is going to work and be part of my solution set. And then lastly, you're going to choose something that is bigger than 4. So for instance, let's look at x equals 5. So again, going into our inequality and plugging in 5 wherever we see an x, we want to know, is that less than 0? So I have 5 squared is 25. 25 minus 5 minus 12, is that less than 0? Combining my negative numbers, -5 minus 12 is -17. So I have 25 minus 17. Is that less than 0? No, that's 8. 8 is not less than 0. This is a false statement. And so our solution to this nonlinear inequality is going to be everything that falls between -3 and 4. And since this is strictly less than 0, we're not including those critical values. So our solution set is parentheses -3, comma 4 parentheses, or another way to write that is -3 is strictly less than x is strictly less than 4. So you should also be able to graph this function. We just found those values which set it equal to 0. We found those x-intercepts. We had talked about previously how to find the vertex. So we could find the value where this crosses, or where it changes direction from increasing to decreasing, or vice versa, decreasing to increasing. You can use the fact that that coefficient of A is 1, it's greater than 0. So you should know that your parabola is facing upwards. Looking at this, I could tell what my y-intercept is, which is -12. And then I can either complete the square on my quadratic function, or I can use the vertex formula to find that vertex. I'm not going to worry about finding the vertex at this moment. But notice that we were looking at this value where it was less than 0, and where it was less than 0 is where that graph is going to be below the x-axis, which notice is between our values in here of -3 and 4. Okay, so kind of putting together multiple things that we've done in this class into solving this nonlinear inequality. So looking at our next example, we have x to the 4th is strictly less than 9x squared. So we want to solve this inequality, and let's solve it algebraically. So first step, we wanted to get everything to one side of our inequality. And so I could do that by subtracting 9x squared on both sides. So when I'm subtracting 9x squared on both sides, that is not a like term to x to the 4th. So I'm just going to rewrite it as x to the 4th minus 9x squared is less than 0. So looking at this now, I noticed that x to the 4th minus 9x squared, they both have a term or something in common that I could factor out of here. I want to find out when this is equal to 0 to find those critical numbers. And so I'm looking at when is x to the 4th minus 9x squared equal to 0 to find those critical numbers. I notice that they both have an x squared in common, so I can factor in an x squared from both of those terms. If I pull out an x squared from x to the 4th, you're left with an x squared minus, and if you're pulling out a x squared from -9x squared, you're left with -9. So -9 equals 0. We can go a little further here, x squared minus 9. That is a difference of 2 squares. So I notice I can factor that as x minus 3 times the quantity x plus 3 is equal to 0. So when you're factoring, make sure that you're putting your parentheses in there, because if you're not putting parentheses, then what you're writing is not mathematically correct. So since I factored this completely and it's set equal to 0, then I'm going to set each factor equal to 0. If this was factored and it was not set equal to 0, we could not set it equal to that number. That's mathematically not correct either. And so it has to be factored and set equal to 0. So you're looking at when is x squared equal to 0, and you're looking at when is x minus 3 equal to 0, and when is x plus 3 equal to 0. Well, x squared is equal to 0 when x is 0. X minus 3 is equal to 0 when x is 3. And x plus 3 is equal to 0 when x is negative 3. Once we find those critical numbers, which we just did, you want to place those on the number line. So smallest to largest, I'm looking at negative 3, then 0, and then positive 3. And if I look at this right now and look at how many intervals I have in between my critical numbers, or on the other side of my critical numbers, I have, just count them. We have 1, 2, 3, 4. So I have 4 separate intervals that I need to test to see if this makes my inequality true or false. So when I had done that last problem, I plugged it back into my original function. If you want, we can technically rewrite our inequality in factored form. So I could technically rewrite it as x squared all times x minus 3 all times x plus 3 is less than 0. So when we're choosing values, we just want to see, is that value I choose and plug in, am I going to get back a negative number or a positive number? I really don't care what that number is. I just care, is it positive or negative? Is it going to make that inequality a true statement or a false statement? And so I want to choose something which is less than negative 3. So choose any number that's less than negative 3. So I see that x equals 4, negative 4 is less than negative 3. And so if we go back in here, I'm going to put in the factored form, and we plug in negative 4 wherever we see an x in this factored form, we want to know, is that strictly less than 0? So is 0 squared all times 0 minus 3 all times 0 plus 3, is that a negative number? Well, we can do this oops, and I shouldn't have put 0 in here. I'm putting in negative 3, right? Sorry, I don't know why I went in and put in 0. I'm plugging in negative 4 wherever I see an x. So negative 4 squared, negative 4 minus 3, and negative 4 plus 3. I was seeing I made an error once I was looking at the 0 and getting zeros. Anyways, so I really just want to know, is each piece positive or negative? So if I square negative 4, I notice that that's positive. My negative 4 minus 3, I notice that's a negative number. And negative 4 plus 3, I also notice that's a negative number. And so if I multiply a positive times 2 negative, is that still less than 0? No, because a negative times a negative is positive, and a positive times a negative, positive times a positive is positive, and is a positive less than 0? That's false. So I know any number that was less than negative 3 is not going to be part of my solution set. So now I want to choose a value between negative 3 and 0. Fortunately, 0 is not part of my value in between there, and so I want to choose a number that falls in between there. So what about negative 1? So going in here, wherever we see an x, we're going to plug in negative 1. So we have negative 1 squared -1 minus 3, and then we have -1 plus 3. We're asking ourselves, is that less than 0? Well, if I square a negative, that's positive. A positive times -1 minus 3, that's a negative. -1 plus 3, that's a positive number. Oops. Is that less than 0? Yeah, positive times a negative is a negative, and that negative result times our positive is also negative. A negative less than 0 is true. So I know any number in between -3 and 0 is part of my solution. This is where my graph would be if I graph this below the x-axis. Choose a number between 0 and 3. So how about x equals +1? Dropping in +1 wherever we see an x. You can do it in the factored form, or you can plug it into the original and see if it's true or false. If you really want to figure out what those values are, you can. But I'm just curious, is my value going to be positive or negative when I plug in my negative, when I plug in my +1? And so I have 1 squared, all times 1 minus 3, all times 1 plus 3. Well, I know 1 squared is a positive number. 1 minus 3 is a negative number, and 1 plus 3 is positive. So I have a positive times a negative times a positive. I notice that's a negative number. And a negative number is less than 0. So this is also true. Choosing a number that is greater than 3. So let's look at x greater than 3. So x equals 4 is a number greater than 3. So if we square 4, and then we do 4 minus 3, all times 4 plus 3, is that less than 0? So 4 squared is positive. All times 4 minus 3, which is positive, times 4 plus 3, which is also a positive number, is a positive times a positive times a positive less than 0. That's false. Positive number is not less than 0. So notice -3, +3, and 0 were x-intercepts. Notice that our x-intercept of x equals 0 had a multiplicity of 2. So we talked about what's happening on the graph of our x-intercepts if our multiplicity was even, which 2 is. It was just touching the graph and turning back around. So technically, I know then by what I'm looking at is that I'm below the x-axis and touching the x equals 0 and then going back below. I know somehow I'm going to be crossing at -3 and then crossing at +3. So I have some graph, that's a very general sketch of what I would have of that polynomial if I sketched it. And so for my solution, we have not including -3, so parentheses -3 to 0. I'm not going to include that because I don't have the equal to part of my inequality. So parentheses union, parentheses 0 to 3. Or we could have written that as -3 is less than x is less than 0. Union 0 is less than x, which is less than 3. So we just solved that nonlinear inequality algebraically. So looking at one more example, and this is a rational function inequality. We have x plus 5, that quantity is squared, that's in the numerator, and that is all over the quantity x squared minus 4, which is in the denominator. That rational function is greater than or equal to 0. So first step was to get everything to one side of the inequality, already done. The next step, if it was rational, to rewrite it as a single fraction, it's already done. We want to find out where this was equal to 0, and we want to find out where it's undefined. So we want to find out where our denominator is equal to 0. And so I know that x plus 5 quantity squared equals 0. Well, if I took the square root of both sides using the square root property, so I would have the square root of x plus 5 quantity squared equals, don't forget that plus or minus in front of the radical. In this case, it doesn't matter, but in other cases it does. And you would be missing one of your solutions if you didn't write that plus or minus in front. So square rooting a square, that leaves me just with x plus 5 on the left equals plus or minus the square root of 0 is 0. So I just have 0. Subtracting 5 on both sides, I get x is equal to negative 5. I notice that factor up there, x plus 5 quantity squared. That is an even multiplicity. So I know my graph is going to be just touching at x equals negative 5, but not crossing. So that could help you when you are deciding which intervals are true or false. We also had to see where it was undefined, and that was where x squared minus 4 is equal to 0. This would not be part of the domain. So you can either use your square root property or you can factor this. The difference of squares, x minus 2, x plus 2, set each factor equal to 0. We get x equals 2 and x equals negative 2. Looking at that, those are odd multiplicity. So I know graphically that I'm crossing the x-axis at 2 and negative 2. Place our critical numbers, which we just found on the number line. We have 3 critical numbers. One of them is defined, 2 of them are not defined. We have negative 5 is the smallest. Then we have negative 2. And then we have positive 2. So looking at this, I have 1, 2, 3, 4 different intervals I need to test. When we test our values, again, we can plug in values into this. And we can just think about positive and negative numbers if we would like. Or you can plug it into, let's even do it better. How about x, x plus 5 quantity squared? Well, I know that's always going to be a positive number no matter what. And then I have factored form x minus 2x plus 2 greater than or equal to 0. So choose something which is smaller than negative 5. So if I chose x equals negative 6, negative 6 plus 5 quantity squared, that's positive. Negative 6 minus 2 in the denominator is negative, and negative 6 plus 2 in the denominator, that's negative. Is that greater than or equal to 0? Yeah, a positive divided by a positive is greater than or equal to 0. So this is true. Choose a number between negative 5 and 2. And negative 2. So a number between negative 5 and negative 2, how about x equals negative 3? So negative 3 plus 5 quantity squared, that's always going to be positive. Negative 3 minus 2 is a negative number. And negative 3 plus 2 is also a negative number. Is that greater than or equal to 0? Yeah, a positive over a positive is greater than or equal to 0. So this is also true. choose a number between -2 and 2. So I see x equals 0 works. So 0 plus 5, quantity squared, is positive. All over 0 minus 2 is negative, and 0 plus 2 is positive. Is that greater than or equal to 0? No, a positive divided by a negative is not greater than or equal to 0, so this is false. Choose a number which is bigger than 2. So if I look at x greater than 2, how about x equals 3? 3 plus 5, quantity squared, is positive. All over 3 minus 2 is a positive number. Times 3 plus 2, which is also positive, is that greater than or equal to 0? Yeah, that is. That's true. So I'm going to include my critical numbers that set the numerator equal to 0, but I cannot include the values which set my denominator equal to 0 because those are undefined. And so I'm looking at everything from negative infinity. I can include -5 to -2. And then I'm looking at everything that is bigger than 2. Okay, so -5 set it equal to 0, and 0 is greater than or equal to 0. So for our solution set, we have negative infinity to -2, parentheses, union 2, comma, in parentheses, to infinity, parentheses. So x could be strictly less than -2 and it's part of our solution, or union x could be greater than 2 and also be part of our solution. Okay, so there is solving nonlinear inequalities and rational inequalities, both graphically and algebraically.